And finally, the typing of the functions. Here are the rules that we use for typing functions. So first, before doing that, I should recall you the old type system we had for our mini-while language. It's made of two parts. The first part is quite easy. It's just we from the type declarations, we infer a mapping, a table of association between variable names and basic types. So this can be done, for example, with the two following rules. I won't detail them because basically what you just do is that you inspect all the declarations, and for each of the variables encounter them, you create something of the form x to t, where t is a type. Then you have a typing judgment for expression, like that checks that you add integers and stuff like this. So this is one typical judgment for the addition. And then you type the statement. They have no type. Not that you don't check them, but the statement, the type checker for statement looks like this. You just take the statement S is well typed in the typing environment gamma, and it has no type because there's no type for statements. This is also an expression, so I was missing the expression how to type the variables, and it will be useful in the next steps, as you can imagine. If you want to type function body, which was only the main function body before, if you want to type the main, then you do that. That is, you just produce a typing environment from the declarations, and then you use it to type the statement. Typing sequence is typing each part of the statement. Typing an assignment requires you to have the same time for the variable and for the assigned expression. Okay, and typing a conditional just check that the condition is an if the if is a boolean, and then just checks both statements while it's similar. Now, to be able to type functions, I first need to extract a list of function signatures. So I need a mapping from function names to their type. I will write their type in the following form, which is this is a type for a function that takes n parameters, so the number is important, of type to1 to n. So this, you can imagine this is integer boolean, for example, and this is the return type. So this means I have a function f of name f that has this signature to signature of function, and this is inferred directly from the method declaration, the first line of the method here, from the nothing much special here, and you can, this just says that you can, and the second rule just concatenates the definition of all functions. So if you take any two function definitions, you will recursively enter inside each function definition and produce different list of function signature function tables. And you will put together different function tables. You just require that if you put together two function tables, they have different domain, which basically means that you cannot define two functions with the same name. Okay, now let's type programs. Now that we have an environment with a table of association for function, we can start typing statement. So a typing of statement will have the form gamma, where gamma is a map that defines the variable types, gamma f, which is a function map that we've just defined, and s is a statement. So basically, this just says that the statement s is well typed in a context where I know the functions of gamma f and the variables of gamma. So to type a program, we type all function bodies. So remember, a program looks like this: a set of global variables, a set of function, and a main body that has some local variables for the main and a statement for the main. To check this program, I first check that I first generate a typing environment from the global variables. Then I'll generate a table of functions from the function definition. Then I generate a local, this is the local typing environment for variables for the main statement S. So now I can type check the statement S by using global and local variables to S and the function table. Okay, that's it. And now I just need to check all the functions that are inside the definitions. And for all of them, I'll just check their their body. So what I do is that I take all, so this is a function definition. If you check the syntax, it has this chain. So I take all the function definitions that are inside fundef, they all have this chain, and I want to check that SF is well typed. I also want to check that the expression put in the return statement is well typed too. And that's basically what the line below does. First, I want to check that the return statement is well typed, and it must have type 2, which is here. I said that I changed the signature for the type checking of statement, but not of expression. Expressions don't care about function calls, at least in our small language. So to type a function, I just need a typing environment for variables, which necessarily is made by the global variable plus the local variables of the function. So that's how I type E. And now I just need to type the body of the function. And I do it with exactly the same kind of typing environment, so global and local variables plus table of functions, because now inside the body I can call other functions. If you look carefully inside this expression, I didn't define the local typing environment for variables, which is this gamma L here. And simply generated from the local variables of the function f, plus, of course, the typing of each of the parameters. And that's it. I purposely didn't express exactly what was this global plus local environment. And how do you define a global plus local environment? Is simply you take the variables that are defined globally and you override it by a local variable typing map. So basically you just want gamma g plus gamma l of x to be gamma l of x if gamma l of x exists. And if gamma l of x doesn't exist, then you take inside gamma of g. Said other way, if you look at this, ensure that, for example, in my example here, when I look at this x, I'll check the type that is defined locally this way. And if it was not defined locally this way, like here, there's no local variable, so it will get back to the global variable here. Of course, you know the typing of all statements that we had before, but you don't know how to type the function call itself. How do we type a function call? So suppose I have a statement that is a function call, and now I want to type it. Well, that's quite simple, because I know the signature of the function f. It's given to me by gamma f here. So I check this, and gamma f of f will give me something of this shape, which is a function that takes n parameters of type 2(1) to 2n, and returns the parameters of type 2. So to be able to conclude this, I need all the hypotheses to be true. And in particular, I need this n to be equal to this n. So I need to have the right number of parameters. And then for all the parameters, they need to have the right type. So this is expressed here. I check the name of the type of the expression passed to the function, and they all must have the type of the declared parameters. And finally, I must just check that at the end of the function, this is the type of the returned expression, and it must be equal to the type of x, because I want to store whatever is returned by f into x. Before giving a conclusion to the course, I want to give you a few advices on the implementation of the typing of functions in the Mini-C language you will do during the practical sessions. So basically what the typing of function should do, what we presented here, is that to check that parameters are of the good type, but also the number of parameters is good. That is just what I presented in the rule. In Mini-C, because we don't go through the program several times, We have function definitions and function declaration. In the sense that you can declare that later you will define a function so that the type checker already knows that there's a function with its name foo, typically. In that case, the declaration has no body, and if you have a declaration, or you can have several declarations, but a single definition for each function name, and all the declarations and the definitions must match with the same type, both for parameter and for return type. So as we have this possibility to have function declaration, we don't need to pre-populate the table of function types. We can just build it at the same time as we go through the program. And of course, you shouldn't forget to check the return type, and in particular, the place where the function is called. So to conclude about this course, we've looked at many semantics to specify function behaviors. And while I consider that this mustn't be taken as built-in semantics that are the perfect solution for this thing, even if it works well and it's very close to what the semantics you would find in the literature. But we solved several problems that I find important, and I think getting inspiration from the way we've solved those problems is a nice thing to remember from this course. We've seen how to stack environment and to deal with scope of variables in very different ways. Some were more constructive, some were a bit easier to write. And in the scope of variables, the key part is to be able to restore the right environment after invocation. We managed to also to deal with return value, and each of the semantics has its advantage and to corresponds to some of the semantics encountered in literature. The most advanced semantics that I showed you is not necessarily the one you want to implement for your language, because if you're not too much concerned by the link with the compiler, perhaps one of the first two semantics are a bit easier and perhaps easier to reason about too, and easier to prove properties. All of those semantics are interesting. You should just pick the one that fits with the need you will have. Finally, we didn't spend time here to work on proofs. The good follow-up of such a course would be to prove that the typing is good for the function invocations, and we maintain the properties of typing we had before, which is progress and safety. Okay, thank you for listening, and I hope that we'll have a bit of time for questions or further explanations.